Hi, everybody. As Amanda said, I work with GALAHs, which doesn't mean that I'm a zookeeper, but I do work with something that's called Galactic Archaeology with Hermes. And the idea of this survey is to excavate or to recover the history of the Milky Way. And this is a topic that has interest, or that a lot of people were interested in. One of the great pioneers of the work on stellar spectroscopy, for example, is Annie Cannon, as you see on the top left. She really helped to classify hundreds of thousands of stars, and that is exactly what we aim to do with the help of stellar spectra, with our much higher resolved spectra, however. And the thing is that if we think about the formation of the Milky Way, it's like a big story, and we need to invest a lot of money and really have the best tools to do that, to really tell this story. So we've spent a lot of money, built amazing instruments, took lots of pictures, lots of spectra. The problem is we can only observe the Milky Way as it is now. So we only know actually how the Milky Way looks like at the end. We're missing a lot of the key pages of how the Milky Way formed and evolved. But that's exactly what we're interested in. So how can we recover these missing pages? The great thing is that the Milky Way is one of those galaxies where we can actually resolve billions of stars. So I'm just zooming in here on one small pattern on the sky, and you see a lot of stars there, and including an open cluster of stars at the top, Messier 67. And we can actually take spectra of these stars, for example. And even better, a lot of these stars, if they're low mass enough, so less than 2 solar masses typically, they really live for a very long time, billions of years. And to put this into perspective, the Sun already is 4.5 gigayears old, and the Milky Way, or the universe itself, 13 point something. And these stars live really long, so we can really use them to explore our Milky Way over a long time with these stars. And in the best case also, we think that when stars are born, they basically lock their birth material inside of their atmospheres, and we can then use them, even though they move around, to really recover the birth conditions and use them as kind of time capsules and fossils. And that was the whole idea of the field that I'm working in, which is called Galactic Archaeology, using these stars as fossils. So what actually can we use from these stars as information? The one thing that we can do is we can monitor their positions and their velocities. That is one of the things that the Gaia satellite, that I'm pretty sure everybody has heard of at least, is doing. So it's basically monitoring the positions, and by doing that, a lot of times it can also get the trigonometric parallax, which allows us to get a distance. So that's this pi, or var pi in LaTeX. And we can also measure the proper motions of these stars, how they move. And with, for example, information from spectra, we can also complete this information to get an idea of the three-dimensional velocities of stars. And that ultimately helps us to put everything into perspective in a galactic sense. So we can get something that extragalactic people are more used to, something like galactocentric radius or distance from the galactic center. We can get something like this Z, which is the height relative to the galactic plane. And in addition, we can also calculate more conserved orbit quantities. If we, for example, have an idea of how the Milky Way potential looks like, and we do have a rather good idea nowadays, we can really figure out what are the orbit energies, what are, for example, the eccentricities of stars. And that is more useful than just having a velocity, because you can imagine that as time moves on, the velocities of stars will change. However, these more conserved quantities, including the integrals of motion, something like, for example, the angular momentum of orbits, that is something that stays more conserved. So we have a much better idea of how we can quantify orbits of stars with just these integrals of motions. In addition, we can also observe these different stars with different filters. We do photometry, so we can look how much light is coming in the blue or in the red. And if we look at the difference between different filters, we can put that in the x-axis as a color, where redder stars are typically cooler, bluer stars are hotter. And we can also get an idea of the luminosity, or how faint or how bright stars are. And you see that for this particular case of M67, these stars follow a very interesting pattern of different evolutionary stages that they are in. And that is possible because these stars, especially of this open cluster, have been formed at the same time with a rather similar chemistry. And in addition to getting fundamental parameters like colors and temperatures, magnitudes, luminosities, we can also use our knowledge of stellar evolution to figure out something about hydrogen, helium, and the metals, so everything that's heavier than hydrogen and helium. And in addition, we know that we can also get, with the help of, for example, isochrone fitting ages, masses, and radii. And the one thing that I'm interested in is actually getting information out of these stars if we do spectroscopy. So one of the things that we can do is we can look at how abundant certain elements are, which you see in the absorption features here. Before I continue, how many of you are actually spectroscopists? 1? 2? All right, half of the room. Okay, in that case, I might actually also include a bit more of the introduction to stellar spectroscopy. For the people in the back, you don't have to listen to that part. But I hope I will still make it interesting, because we've learned a lot about the Milky Way. So if we look back to what William Herschel thought the Milky Way looks like, he actually looked at this and thought, okay, the sun must be in the center of the galaxy. We know that's not actually quite correct. Kim Van came and she actually did this sketch to look, which looks a bit more correct. So we have figured out by observing huge parts of the galaxy that actually we have in the center a bulge, we have a lot of stars moving on a disk, and we do have stars with more random motions that actually follow kind of a halo. And another thing that we also figured out is by just doing star counts with the Gaia satellite. So if you observe more than 1 billion stars and just look at the densities of stars, one of the things that we can actually now measure and not only predict is that we have a Milky Way bar. And in addition, we can also see that this bar is rotating. And all jokes aside, that leaves us with some main stellar components. So we know that we have a bulge with a bar, a disk, and a halo. But it's getting, of course, more complicated, as always. If you start to count the number of stars in the disk as you go away from the galactic plane, some of the things that we have, or that people have found in the 80s, is actually that as you do a number count, so where the x-axis is your logarithmic space density and your y-axis is the distance from the plane, you can actually fit this profile best with 2 exponential functions, which means that people came up with this idea that we have a thin and a thick disk. But why do we have 2 disk populations in our Milky Way? One of the ways that we can possibly figure that out is by actually looking at the elements in these different stars and figure out their origin, which then hopefully can help us to figure out if these 2 different disk populations possibly formed differently. And I know a lot of people look at a periodic table like this. We all know it from school or Astronomy 101. But this is actually the way that I tend to look at this. That is basically, where can we look to actually measure these elements? Because we have different regions where we have absorption features in stellar spectra from these elements. So for the GALAH survey, when we actually figured out how should it basically be set up, we basically tried to find as many elements to measure as possible. So we decided to go for 4 different wavelength regions to get up to 30 of these different elements. And that can help us ultimately to figure out the origin of elements. And while this is a prediction that Chiaki, including Amanda, did, it is basically showing you the different nucleosynthetic pathways, how you can create different elements. And Amanda would be much better to explain that than me, so I will do the layman's version. So you see in black typically stars that are enriched through Big Bang nucleosynthesis. We have a lot of contribution for some stars from low mass stars, so the green. We have exploding massive stars, exploding white dwarfs, merging neutron stars. You see that different elements here are color-coded differently. And that's good, because if we observe these different elements, we can get a pretty good idea of how they are enriched through different processes. So how does that look like if we look at our thin or thick disk? This is a study that Klaus Fuhrmann did in the 50s with 50 stars. So to keep things simple, on the x-axis, this is a plot that I will show a lot. So I'm just going to explain it this one time in detail. On the x-axis, we have our what is called iron abundance. That's a pretty good tracer of how much metals we have. And we do that on a logarithmic scale because the elemental abundances in stars change on such a huge scale that we typically do that logarithmically and also relative to the sun. So the sun here would be at 0, and an iron abundance of -1 would mean 1/10 of the solar iron abundance. And on the y-axis, we do that with 2 different elements that are enriched through typically 2 different processes. And again, explained very, very easily. we basically have massive stars which basically go off in supernovae type 2, which primarily enrich magnesium. So that means we go up. As a lot of stars die, we typically go to the right. And at some point, we can also have low mass stars die, which then go off in supernovae 1a and enrich primarily your iron, if I'm correct. And that means that you basically go down in this diagonal form. So how does that look now in these 50 different stars? Looking at different parts of our solar neighborhood, Klaus Fuhrmann basically found that we have a lot of stars in the solar neighborhood that are part of this thin disk, or actually around 0, 0 in this diagram. A lot of the thick disk stars are higher enriched in alpha, are a bit more metal poor. And in addition, he was able to estimate the ages of these stars, so large circle means old. And we see that a lot of these dark gray dots are old, which means that we have a thick disk that is typically old, older than 8 gigayears actually, and highly enriched in alpha. We have some stars, 2 stars actually, in this transition zone. And we also have this thin disk at the bottom, which is young and low in alpha enrichment. So how did these two disk populations form? One of the ideas that we can put forward is that possibly they have been formed in 2 different formation epochs. So you can imagine that you at the very beginning have your early Milky Way forming with a lot of supernovae type 2 going on. But what then happens is that at some point you do have a gas-rich merger, which brings in pristine gas. And what that does is that, first of all, this stops your formation of your high alpha sequence or your thick disk star formation. We have a lot of mixing going on, which mixes all the metals. And then we have the beginning of the formation of a low alpha sequence or a thin disk. We can, however, also think about another scenario where we actually have a parallel formation and migration, and only if we can, for example, estimate the ages really well can we tell them apart. But currently we're still stuck with age uncertainties of at best 15%. So typically we actually have 30% age uncertainties, which means you can say a star is 8 billion years plus minus 3. That's a huge range. If you put that on a redshift scale, that's like a really large scale. But the idea of this parallel formation is that, for example, 3 gigayears after the Big Bang, you have some of these early galaxies evolving. And actually, this is a simulation, but we can also find that in some high redshift observations of having some high redshift clumps. And you can think about that these are regions where you have a short and intense high alpha star formation. And what then happens is that you have a parallel formation all throughout the disk, plus some kind of migration, which means that at some point these orbits are going to be blurred out, and then you're left with 2 different disks. Now, which one is true? That's actually still an open question, and I will show you some of the research that we're doing to really try to answer this question. But to give you a recap of what are some of the big questions of galactic archaeology. One of the things we're interested in is what are the building blocks of our galaxy, and how does the Milky Way actually compare to other barred spiral galaxies? I'm personally very much interested in these 2 different disk populations, so I will talk a lot about that today. But you can also ask me about, for example, questions of how does the galaxy or other galaxies self-pollute? How do they chemically enrich themselves? And that's something that I'm doing from an observational side, and especially people in Monash do also from a theoretical side. So that's where our fields come together quite neatly. But the problem is, can we really do that with 50 stars only? So that's what we had 20 years ago. And of course, the answer is no. So we spent a lot of money and actually started what is now also in reviews called the Industrial Revolution of Galactic Archaeology. We've built a lot of instruments, including, for example, the Gaia satellite. And that has helped us to really go from something that we had 100 years ago. So this is one of the first versions of what is called the Hertzsprung-Russell diagram or color magnitude diagram. And you see 150 points here. Now what we have what we have in 2020 now is more than 1.5 billion stars. We really start to go out of the local vicinity of our sun. We really start to explore the Milky Way as a galaxy. We start to also observe stars in the galactic center. We really start to get an idea of how the Milky Way actually looks like, and what interesting and weird stars live in it. And we do that not only with a satellite, of course, but this is a global effort. We have a lot of different surveys, so not only the Galactic Archaeology with Hermes survey, which is, of course, in Australia, but we also have a lot of colleagues working, for example, in Chile, number 3 here, which observe with the foremost telescope soonish, and they will actually observe 10 million stars. Now, this all leads to not only a revolution in the instrumentation, but also one of the things that we really try to do now is to observe stars with different instruments. So one of the things that we, for example, do as part of the GALAH survey is we try to get a really good coverage all over, but we also follow up, for example, here shown in green and red, observations or footprints of telescopes that are spaceborne. So, for example, the TESS or Kepler satellites, which take really good photometric measurements, continuous photometric measurements, to get information, for example, of oscillations in stars that can help us then to pin down their masses and radii better. We also have a revolution in technology. So when we observe from Siding Spring Observatory in New South Wales, we do that with Australia's biggest optical telescope, the Anglo-Australian telescope on the right. And at the top end, we have, or amazing engineers actually, have built a fiber positioner that allows us to move 400 fibers at a time to observe 400 stars at a time. That's something that 100 years ago people couldn't do. And what that allows us to do as well is we can feed that into this amazing high efficiency spectrograph and observe a lot of stars at a time and get in the top left these amazing spectra in different wavelength regions that we have optimized to get as many chemical abundances as possible. And the great thing is that this is really leading to this kind of revolution in the spectroscopic quality. We never had so many spectra with such high resolution in all of these different wavelength regions for so many stars. This is really something that now is also, of course, putting or giving us some challenges, and I will explain in a bit which challenges we can see. But I just want to first of all convince you that these spectra are amazing, but also they change a lot. So there's a lot of information in there. As we, for example, look at a star that is born at an age of 4.5 gigayears, has a similar composition to the Sun, we see that spectra along such isochrones or different, with different masses change a lot. So that means that we actually have one of the challenges. We don't only have stars that look similar to the Sun, so we can basically analyze them with a similar setup to the Sun, but we also have a lot of stars that are very, very metal-rich. And this is just an example of a metal-rich star. If they are getting even more metal-rich, then we have so much absorption happening that we start to have a problem that we have actually too much information, because these lines start to get blended, we can't resolve them anymore, and that's causing all kinds of problems. But we can also go to the other end and look at the stars that, for example, Andy loves, these metal poor stars. And you see that basically the only absorption feature that is left here is hydrogen. We don't have enough absorption features left for all the other elements that we're actually interested in, because that helps us to constrain the low mass region of stellar chemical evolution. So we can have either too much information, which causes degeneracies, or not enough information to really estimate what we're actually looking for. Another problem is that doing, for example, classic spectroscopic analysis with spectroscopic or spectrum synthesis based on atmosphere models and radiative transfer, and doing like the whole set of proper spectroscopic analysis is computationally quite expensive. And a lot of people, including, for example, Andy, have worked on making this more efficient, making this computationally cheaper. And what we have done then is we've used this amazing work that both Melissa Ness for the Canon and Andy for the Canon as well, but also Janssen Ting for the PAIN have done, is we developed pipelines that analyze spectra of GALAH by combining a classic spectrum synthesis for a small but representative and high fidelity training set. And we train basically a spectroscopic model. So we use this high fidelity training set to figure out, okay, how does the spectrum change as a function of different stellar parameters? And we don't do that with radiative transfer anymore. But what we do now is we come actually up with such models. This is just a very generic form. And we can, for example, put, instead of just generic form, we can use a quadratic model to describe how flux changes. So to make that a bit more easy to understand, we can start, for example, with our average spectrum. Let's say a star looks very similar to the Sun. How does a spectrum change if we increase or decrease the temperature? Well, luckily, not the whole spectrum changes, but it's changing in a very specific pattern. And we can also ask, okay, if we increase or decrease, for example, the amount of metals in a star, how does that change? And we get this very specific response in the spectrum. And luckily, we can also look at the different elemental abundances and ask ourselves, oh, I'm really interested in manganese. How does the spectrum change if I in or decrease manganese? And we get a very specific response here, because manganese is one of those elements where we actually have 6 different lines in this specific region. So we can use this to estimate the abundance of manganese. And that's just one example. We're doing that across 30 elements at a time now. So this is getting computationally heavier. But because we have this amazing machinery, that is computationally still much cheaper than doing full-blown spectroscopic synthesis. Another challenge that we have is that we are only as good as our knowledge of input physics. And one of the things that in stellar spectroscopy we still do a lot, and especially for these large surveys, is we assume that each star is basically easily described as a one-dimensional sphere. And we know that's not true. We have sunspots, we have stars doing all weird things in actually 3 dimensions. So we would have to do that properly. Another thing that we have to think of is that we typically assume that basically each layer of a star is in local thermodynamic equilibrium when we have our lines forming. That is also not true for all stars, and that's especially not true for a lot of very hot stars, and that's causing problems. So on the right-hand side, I'm just showing you here how wrong our assumptions actually make our elemental abundance estimation for oxygen. So this is a logarithmic pattern, so minus 0.5 means a factor of 3, that we're basically overestimating our oxygen. And on the left-hand side, you see that we have some oxygen measurements of solar-like stars that we think, or that basically if you do it in a local thermodynamic equilibrium, they're an oxygen abundance of 1, but that's way too high. We actually, if we do it properly, they actually go down by a factor of 3. And that is something that we have a lot of people in our survey, including Anisha Marcy, but also Karin Lind and others, working on, who really do amazing work on telling us how can we actually take these departures from local thermodynamic equilibrium into account and get accurate and precise abundances. But that, of course, only works if we have a good spectrum. And even worse, that only works at the moment if we really have a single star that we observe. But a lot of stars that we observe are actually binary stars. The problem is if we observe 1 million stars, we can't look at all of these spectra unless we have a lot of people who really volunteer to look at like 100,000 spectra. But I can tell you it takes a long time. So one of the things that we actually did is we started using more interesting sorting algorithms, I would say. And one of them is called the T-distributed stochastic neighbor embedding. I'll not go into the details, but just to briefly explain, what we want to find is stars or spectra actually that look very similar, so that we can group them together and say, if we, for example, know that one star is a spectroscopic binaries with split lines, we want to just find spectra that look very similar, because then we know those must also be spectroscopic binaries. And this T-SNE approach actually does exactly that through a more complicated algorithm. But just to show you how that works, we basically get an idea. This is three different color codings of the same map. So what basically happens here is that stars or spectra that look very similar are close together. The more they look different, the further they are away. And you see, for example, at the top left of this temperature color coding, that the hot stars are all grouped together. They have very similar spectra. And we can use that, for example, to also find binary stars or stars that, for example, have emission lines in some of these features that we're looking for. So that's amazing, because that really helps us to not have to look at 1 million spectra to figure out which are the weird ones. Another thing is that we basically have now done that. Well, the GALAH survey has started observing in 2013, and we have published more and more data as we went. So in 2017, we had the first data release with only 11,000 measurements provided, and we've worked a lot in 2018 to provide 340,000 spectra. That's a significant multiplication of the spectra or measurements that we had available, and we also have 23 elements now. And the latest data release that is public is now almost 700,000 spectra and 30 different elements. So we really cover 1/3 of the periodic table now with measurements. And we're, of course, continuing to work. We continue to observe. So GALAH DR4, which I'm currently working on, and we hope to publish it by the end of the year, will have almost 1 million stars observed. And we've also done one better. we have 31 elements, and we have included one element that we thought wouldn't be possible. We are now able to measure nitrogen in GALAH as well. So we cover C and O. That is part of the elements of life, and a lot of other people are really interested in that. So we're very happy that we now have nitrogen measurements. And if you have questions about nitrogen, feel free to ask me. Otherwise, we can have a chat afterwards. But ultimately, we really cover a lot of these different stars, and we can learn a lot about how galactic chemical evolution works as we see it as observers. And so you can, for example, look at lithium, for example, very nicely produced by the Big Bang nucleosynthesis, but it's a very complicated element, as I will show you in a second. We can look at sodium and magnesium, which are typically coming from these massive stars. We have manganese, we have barium, we have europium. So we really cover different nucleosynthesis pathways. And luckily, all of these different pathways really produce different abundance patterns. So I'm just going to show you iron abundance versus the abundance of these particular elements. And the main takeaway here is that they all look very different. And I will not be able to go into the details, but I just want to show you at least 6 of the elements that we have. So starting with lithium. That already looks very interesting because it's covering such a wide range of different abundances. We can, for example, compare that to sodium, where a lot of the stars that we observe in GALAH are part of the solar neighborhood. They're typically thin disk stars or low alpha stars. So they have typically abundances of around 0, 0 in this plot. We can also look at magnesium, which is again having a different pattern. We can look at manganese, which is produced by supernova type 1a. So they need a longer time to actually be able to produce manganese, which then goes up as we go to more metal-rich stars. We also have barium and europium. And the good thing is that these patterns all look very differently, so we can learn a lot about stellar chemical evolution. And going back to lithium, it's one of those very interesting elements that also people at Monash have done a lot of research on because it's so complicated. There's so much we can explore. I just want to highlight one of the results that I personally think is quite amazing coming out of GALAH, and that is looking at the lithium abundance of the oldest stars. For the oldest stars, or basically as close to a Big Bang as possible, we have a pretty good prediction from cosmology of how much lithium should have been produced in the Big Bang nucleosynthesis. And the value is 2.75, just to give you a number. Now, when we go to the oldest stars and actually measure the lithium abundance, we measure a lithium abundance. This is a logarithmic scale of 2.2. So that's a factor of 3 below what we would need. So is cosmology wrong? Luckily not, as far as we know. The problem is actually a bit more complicated because we have not really been able to measure a lot of these lithium abundances until we started doing GALAH and other surveys that really measure lithium on such a large scale. So instead of only having 100 measurements, we can measure now hundreds of thousands of lithium abundances. And we can look again at this temperature surface gravity diagram, or like a spectroscopic version of the Hertzsprung-Russell diagram. And we can look at different regions of this and look at how the abundances of cool stars in the bottom right look like and the abundances of warmer or hot stars on the top left. And if we look at the average abundances of these two different regions, they're actually not the same. They're systematically different. These warmer stars have systematically higher lithium abundances than the cooler stars. And the difference here is actually a factor of 3. And if we basically would extrapolate that all the way down to the coolest or the most metal-poor stars, that could potentially explain exactly this difference that we see. So that's one of the predictions that we have. The problem is you can't measure old, hot stars that are metal-poor. They basically would have evolved already and would have burned their lithium. So this is why this is just a prediction and not a proof yet. But I think as we continue looking, maybe we'll be able to at least extend this towards more metal-poor stars. The great thing is that we can not only use lithium. We have such a good coverage of elemental abundances and also spatial coverage now thanks to GALAH and thanks to Gaia. So we can really start to explore our galaxy in different spatial bins. And I'm just showing you here one of the most interesting results that is coming out actually of the Apogee survey that Michael Hayden was involved with. And if we just look at the solar neighborhood, so just this orange box with the sun in the middle, you can see at how these abundances look like. So we have our iron abundance and an alpha abundance, which is basically elements like magnesium, silicon, calcium, titanium, possibly not titanium. Cherky always tells me it's not titanium. But that's a different story, sorry. Getting back to the main story. We have this typical abundance of these stars that are similar to the sun around 0, 0. Now, if we go to the inner galaxy and the outer galaxy, we're just going to expand to these two boxes here, and we can actually start to see that, for example, the iron abundances change a lot. Right? We see that iron decreases with the galactocentric radius, which means that we most likely had a slower or later star formation in the outer thin disk. The great thing is that, for example, Christina Eilers has also now been able to produce a map in more of a face-on view of the galaxy. And you see this color coding from the iron abundance clearly shows that we have this gradient also when we look at the face-on. So we definitely had some gradient happening, but possibly we can also see that in the middle panel, we possibly have some visitors from the inner and outer boxes, which would suggest that we have some kind of radial migration happening. And to get that in a more global sense, I'm just showing you in a second the full-blown picture. So we're not only having these 3 boxes now, but I will show you a lot of different boxes that go in different galactocentric radii and different galactocentric heights. And you'll see that this abundance pattern changes a lot. And there's a lot of information in there. I will just ask you to look at specific parts as I will explain that. So one of the things that we can see is, especially if we look at the top left, we have a lot of these stars that are actually high in their alpha enhancement, and they have a rather similar iron abundance. So we have a very high star formation rate in the inner disk and in early epochs. And we have also a lot of, if you look at the bottom part, we see that most of the stars that are close to the galactic plane are actually part of this low alpha disk. So that's where they're dominating. And we see that at lower galactocentric heights. But as we start to go and look at the top right, this is a region that is typically far out and far up or far below. And we do see that these low alpha stars are still there, which is evidence of something, and I will show that for the Zoom people as well, is basically like some kind of a flaring that happens, that our disk at the outer edges starts to flare. So what can we learn about, so this is basically what we can learn about the disk. Now, one of the things that I'm also interested in, and that's why we changed the topic a bit, is the stellar halo. And how is the stellar halo connected to the disk? So we see that if we just look at 50 stars, we only have 4 halo stars, so metal poor stars or stars that have more random motions and don't actually rotate with our disk. Now, in 2010 and the years after, Paul-Erik Nissen and Will Schuster did a study where they looked at more of these halo stars, and they actually found that we have 2 different patterns. One of these patterns that's following the plateau of these 4 stars that we've seen before, but they also found a lot of stars that actually have lower alpha enhancement. They called it the low alpha halo, and they actually suggested, just showing in this graph here, that these are possibly stars that are not born in our galaxy because they have such different chemical enrichment, history. Now, how does that look if out of a sudden we have now 500,000 stars, right? Such a factor more stars. We do still actually see that most of our stars in the local neighborhood are still part of the low and high alpha disk, but we do see a bunch of these stars also in other surveys that are definitely showing this very different chemical enrichment. So is this evidence of major mergers happening, right? If we have a lot of these stars not born in the galaxy, but they're in the galaxy now. So that's actually something that, thanks to Gaia, people have found. And I'm just showing you here an image where we have the early Milky Way in white and another galaxy merging in yellow. And as you see, this merger process continues and continues. And at some point, we're left with our Milky Way in white. And these stars that have been accreted or merged with the Milky Way are now out of a sudden everywhere within our Milky Way. So how can we find them? Well, the great thing is that a lot of these stars do actually still move coherently in some sense. But they don't move coherently with the disk. That's actually one way of how we can find them. They typically have low angular momentum. They're, for example, you can find them in the halo. But also if you look in the disk, you have different ways how you can find them. One of the things is that these stars typically, especially the stars of one of the big structures that has been found and dubbed the Gaia sausage enceladus. These stars have actually typically very high eccentricity, and they have a very large radial action. So basically, their orbits go in a galactocentric radius sense very far out and in. And this is one of the ways that, for example, Vasily Belokurov, Amina Helmi, Diane Feuillet have looked and tried to identify these stars. I'm just showing you here a plot of the angular momentum versus the radial action. And the Sun is in a region where we have low radial action or low eccentricity. Those are stars with a circular orbit. As you start to be more eccentric, you start to go up. And as you start to have low angular momentum, you go closer to zero. And we have these red stars here, and those are actually these stars that we think are accreted. We can, however, also look at the chemical enrichment, and we know that this must be very different. So if we use elements that trace different nucleosynthetic pathways, we can actually try to basically identify them because they're so far away from the Sun. So what I'm showing on the left-hand side is something that Keith Hawkins and Pyle Das and others have done. They basically looked at the aluminium-iron abundance and magnesium-manganese abundance, and the Sun here is at 0, 0. And in the top right, this kind of blob at the right-hand side, that's the thick disk. And if you look at this red circle in the top left, those are these stars of the Gaia sausage enceladus, or these accreted stars. And ultimately, just to complete the picture, we still have our study from Paul Erik Nissen, who basically said we have this low alpha disk. Now, one of the big questions is, are these actually all the same structures that we're looking at here? Is the chemical and dynamical selection the same? And this is one of the questions that I wanted to answer. But before I go to this, I just want to show you that actually we really believe that this must have been a massive merger, because you can try to estimate at the time when the merger happened, roughly 8 to 10 gigayears ago, how massive must it have been. And you can do that by comparing, for example, the chemical patterns of the stars that we see now with something like the SMC or LMC, and it matches pretty well with the LMC. And based on such arguments, you can say that most likely the merger was on a ratio of 1 to 4, or if you compare with how you can create such patterns in cosmological simulations, you basically come up with a mass of the dark matter of 1 to 2.5. So I hope that convinces you these numbers are quite significant. This must have been a massive merger. But that, of course, only works if these are all really the same patterns, if it's basically one big structure and not several smaller structures. So that's one of the things that I tried to figure out in one of my latest papers. Basically, if we use different selections, do we still select the same structure? So one of the things I did is basically recreate with the GALAH data set the selection that we have done in dynamical space, where they pop up in this rectangle, but then also compare it to the stars that we can select chemically. And now the important plot that's going to pop up is the one that is basically showing the orange plots overlapping with this red triangle. And if we basically have the same substructure, then they will be all in this triangle. But as you can see here, a lot of these stars are not in the triangle. Only 30% are in this triangle, which means that we're losing 70% of the stars that are actually not part of this dynamical selection. So that's a significant mismatch of these two structures. And that is something that we really have to follow up in the future to figure out if it's one big structure or if it's possibly an overlap of several others, or if we have a significant interaction during the merger of this Gaia sausage enceladus structure and the Milky Way. And one of the indicators of that is that if you look at the dynamical selection and look at the chemical abundances of this, you do start to see that we have a significant overlap of the old thick disk and this merger structure. So most likely there has been some mixing going on, and we really have to start to disentangle if that means that we have an overlap of these structures or if we're just significantly contaminated. And on top of that, of course, we always have to decrease our uncertainties, and that's something that I'm working on as part of the GALAH collaboration to get better measurements of these abundances. So what will be the next steps? If we put the Milky Way in context, that is something that really will help us in the next, I'm pretty sure, decade, to really make a lot of progress to figure out the Milky Way as one of the many galaxies that we have. The great thing is, for example, with the MUSE instrument, which is on the very large telescope in Chile, we can take a lot of amazing spectra of other galaxies now. We can't yet resolve individual stars, but we're getting pretty close. We can really disentangle specific regions of galaxies. And the great thing is that because we have such spectra now, we can also get an overall idea of the chemical abundances of some of these stars. And we can also, because we have this, we can do that in a dissection of the radial and the vertical height as well. And that is just something that I want to briefly show. This is basically what will happen more in the future, that now in the black contours, those are the same panels that I showed you before from Michael Hayden, this very complicated, like 20 or so box plot. So this is what we look at in the Milky Way. But now we can actually compare this to other galaxies for which we have been able to measure the alpha abundance and the iron abundance. And we can really start to compare this and figure out how significant are other galaxies showing, for example, low alpha or high alpha disks in which regions of these galaxies. In addition to that, we don't only have more measurements of extragalactic sources, but we also have better and better cosmological simulations. And one of the great things that we can do is we have a lot of these cosmological zoom-in simulations with rather high resolution that now start or get better and better chemical enrichment models. So we basically always, as soon as Amanda and other people have a better input for how chemical enrichment works, we can now feed that into such cosmological simulations and get a better idea how in other simulated galaxies chemical enrichment works. And we can start to compare that, for example, to our own galaxy. And the hope is that at some point we get a better and better agreement. So at the moment in these contours, I'm showing you here observations from the GALAH survey for the Milky Way and a simulation of a Milky Way analog. This is not exactly the same because most likely the history of these two different galaxies is not exactly the same. But you also see significant differences that some of these galaxies are more metal rich or metal poor. But the big takeaway here is that we can start to really see different chemical enrichments in cosmological simulations, and we can use that to really get an idea of how different formation scenarios of the Milky Way, or how possible such formation scenarios are or are not. And one of the amazing things that, for example, one of my students is looking in is to compare, for example, such simulations with observations of GALAH in a different way. So what I'm showing you here is age metallicity relations. They show you clear sequences of different parts of a galaxy. The strongest sequence that you can see here in yellow most of the time is actually a typical low alpha or thin disk that is evolving. And that has this clear sequence. But we also see a second sequence that stops at an iron abundance of minus 0.5. And that is actually a galaxy that, because we have simulations, we know the merger history, that is actually a smaller galaxy that merged with this big galaxy. And we can then compare such very clear information with what we see in the GALAH survey. And I hope I can convince you that at the bottom right there is at least a lot of information. But I'm also showing you the error bars. And again, as I said at the very beginning, we have age uncertainties of 30%. So these uncertainties here are very significant. Right? So we have to really work, for example, on getting better age uncertainties. And that's, for example, one of the reasons why with the GALAH survey, we start to observe more stars where we can get this age information much better. But in addition, we also get more measurements from extragalactic sources now. So this is a study that Marie Martic did. And she looked at a Milky Way analog. And she actually found that if you go just a bit above or below the galactic plane, you start to see that you have your typical disk up here, but you also start to see a very significantly different part of stars that have low alpha and are still very old. Low iron abundances are still very old. So these are at the same age accreted stars that are more metal poor than those that are formed in situ. And that's quite tempting, and we hope to follow this up. And we luckily have been granted a lot of time with MUSE to really follow up a lot of such galaxies under the guidance with PI Jesse van der Sande, where we really try to do exactly such measurements for a lot of different galaxies. And that will hopefully help us to continue this revolution that we have going on in galactic archaeology, where we basically have a lot of measurements of the astrometry or of the dynamics of stars now. But ultimately, to understand evolving galaxies, we need conserved quantities. And those are not only stellar ages, but as good as we can estimate stellar abundances. So that's going to be really the key to figuring out how the Milky Way formed and evolved. And the good thing is that GALAH is actually continuing to deliver more and better chemical compositions, and now for almost 1 million stars, which helps us to really dissect and understand different parts of our galaxy, and including stars that are, for example, formed in situ and stars that have been accreted through different processes. And in the very long run, and that's basically my prediction for the next decade, to really figure out how the Milky Way formed and evolved, what we will do is we'll bring together different fields, and we have to bring together different fields to combine our very local galaxy, galactic archaeology, with the more distant stars and studies of galaxy evolution, and link that all together through simulations to really figure out how the Milky Way formed and evolved. And that's about it. And I'm very happy to answer any questions or collect ideas of how we can do things better with our Galactic Archaeology survey. Thank you so much. Hey, Ilya, do you want to go ahead?
Sure. Thanks a lot for the very interesting talk, Sven. Hope you can hear me from Zoom. So I've seen obviously a lot of these plots, such as the one you're showing on this slide, which show one abundance ratio against another, and there's always a lot of scatter in these kinds of plots. I wanted to understand whether this scatter is predominantly due to observational uncertainties typically, or whether it's really due to some intrinsic fluctuations, because even when some enrichment events happen, they don't quite happen in the same way everywhere in the galaxy, and there's some turbulence, etc. But if so, how good is our understanding of the distribution or redistribution of enriching material? Are we actually able to even talk about average properties in a meaningful way? And if so, I don't even know what the averages are. A meaningful averages when you're looking at these sort of log scale abundances. What do we even mean by some average abundance, etc.?
Yeah, this is an excellent question, Ilya. Yeah. It first of all exposes the problem that I have forgotten to include the error bars. For all the students in the room, you should always do that. But to give you an idea, for example, for the sodium abundance, especially for the metal poor stars, we have uncertainties of 0.2, 0.3 dex for these metal poor stars. So basically already, yeah, the x-axis has significant large uncertainties. And that's something that we really try to work on for these metal poor stars, because exactly, we currently cannot really disentangle if this large scatter that we see is driven by the precision issues that we have, or if it's really something that is intrinsic to the stars, because we had mixing, which means that ultimately we basically have a real mixing of these yellow and green dots. And that's something, yeah, at the moment we still have to work on that. And one of the things I can also tell you is that a lot of surveys, including GALAH, are actually not doing that as good as we should, because estimating such uncertainties for elemental abundances is extremely hard to do. You need basically reference sets of stars in these low metallicity regions where you really know how abundant certain elements are. And that's incredibly tough to do. We have a lot of global efforts going on to produce such data, but we're not there yet. So ultimately, yeah, this is a super exciting question, Ilya. But sadly, the answer is it's complicated. Yeah, I can't tell you more than that at the moment.
Thank you.
What are your uncertainties on nitrogen?
Yeah, so I'm going to give a very technical answer. In the case that somebody is interested in a more overall answer, I can also give that. But to give you a number, right? When we compare with another survey, the Apogee survey, we get a bias of 0.00 dex, but we get a scatter between the two surveys of 0.15 dex. So that's the current scatter that we're working with. To give everybody a reference, that's not perfect. We aim actually for a lot of these different abundances. We aim for 0.02. That is what people tell us we really need to be able to tell apart a lot of different stars. We hope that we can get away with 0.05. So we're not there yet. But since nitrogen is one of these elements that we actually have to analyze, not from atomic features and these absorption features, but from molecular features. So we discovered some very strong cyanide lines in our spectra for like 50% of the spectra. We are able to detect it. So a lot of these giants, we're now able to detect cyanide. So that's going to be interesting for everybody who is interested in C and O abundances in giants. Yeah. Long answer for a very good short question.
You showed it was alpha rich and iron, but how about the art process elements?
Yeah, that's also very complicated. So we know that it's compared to the in situ born halo, it's more lower in the alphas. But when it comes to the art process elements, we're a lot of times actually hitting what we call the detection limit. So it's really hard to measure europium and other neutron capture art process elements in this specific metal pore region. We start to run out of these lines because they're simply getting too shallow. But I can point you to some studies, and I sadly don't remember the outcome. But if you want, I can give you 2 studies that have looked at that, that basically looked especially at europium measurements of the Gaia sausage enceladus. Yeah, but I don't recall the answer to it, so I don't want to give you a wrong answer. But these 2 papers have at least some studies of it.
So if it's too shallow, does that mean there's some hint that is art process poor, or is not that?
Yeah, so I think our detection limit for europium is 0.5 dex, which is rather richer in europium. But then again, this is the region where it's getting really interesting, right? Like we would like to have between 0 and 0.5. That's the region where we would like to analyze more of them. So they're most likely around that region, but we cannot really say if it's 0 or 0.5.
So does that mean that you need to go to a bigger telescope with high resolution than like BLT and?
Yeah, for example, that would be one of the ideas. Yeah, but also you really need to figure out how well you can measure europium in these metal pore stars. Like in general, like at that point we start to also talk about the accuracy, right? Not only the precision, and that's getting tough. Yeah, that's also not my forte. Maybe I'm not sure if other people have a better idea about this particular wavelength, about this particular metallicity range. But yeah, with the GALAH survey, less than 1% of our stars are down in this metallicity regime. So it gets really hard to analyze everything as good as we can.
I remember there was a talk in probably the meeting or something talking about the lithium problem, and I think she was saying it was more of an observational thing, that if you model with non-LTE 3D, the lithium problem goes away or something. But am I remembering this wrong?
No, you do absolutely. You remember this correctly. It's another lithium problem. And there, the problem is that actually, so lithium is not only, like, when we talk about the lithium abundances, we can talk about the lithium abundance of lithium-7 and lithium-6. And those are 2 very different stories. And especially lithium, I think lithium-6 is one of those isotopes that's really hard to measure in stars. And so you have to be really accurate with your modeling. And actually, I think the prediction was that people were saying it's too much lithium measured, but if you do the accurate 3D non-LTE modeling, this disagreement starts to go away. Yeah.
So it's not.
It's a different problem, yeah. But lithium is so interesting. I mean, Andy has written like 10 papers, I'm pretty sure, about lithium, not in this particular region, but also like for example, if you look at giants, a lot of these stars have very low lithium, but there's like 1% or even more that have very large lithium, like really high lithium, above the primordial value even. And we still have to, I mean, there's so many different proposals of why this could be the case. And as we collect more data, and hopefully also GALAH data will get better, then we really can pin that down onto which scenarios really are. Or most likely it's a combination of those, right? So, But lithium is complicated, but I guess that's why it's so exciting.
These Nihao, I'm not sure if I'm pronouncing it correctly, the Nihao cosmological simulations, how many zoom-ins do you have of Milky Way-like galaxies, and how extensive is the chemical enrichment? Like, what elements are tracked?
So I think Tobias has, it's at least 4. I think he's working on more of these Milky Way analogs. I think he's getting to 10-ish. So it's not a crazy amount yet, but you start to be able to look at different analogs. And in terms of the chemical enrichment, the good thing is that Tobias and I were office mates, and so I basically just gave him like a list of elements he should run, and the simulations are running now with all the elements that Apogee and GALAH measure. So hopefully, as soon as these are run, then we'll basically have the coverage of whatever the observational side delivers as well. But yeah, that's still, the simulations are still running. But we start to get more and more. If you have a specific element that you're interested in, then yeah, I can pass that on to Tobias maybe.
Okay, so I think we've hit the hour. So thank you very much again, Sven.
Thank you.